So, these are problems for a system under equilibrium. First one is an example of a single reaction. It is a solved problem in Davis and Davis, and the second one is equilibrium for multiple reactions. Okay. Be aware of the way the ammonia synthesis is written. The delta G is for the way the ammonia synthesis is written. Okay. So, if the reaction was 3H2 plus N2 giving 2NH3, our delta G would be 60. Okay. So, this delta G is for the reaction as it is written. Okay. The question over here that is asked is, you have the reaction taking place and let us say you have various species. You have N2, H2, NH3, and let us say we start off with say X, Y, whatever that Y might be, and 0 moles. Okay. Now, we have the reaction as half N2 plus 3 by 2 H2 giving NH3, and let us say for this zeta is the extent. Okay. If zeta is the extent, okay, simply what amount of nitrogen that is formed is the stoichiometric coefficient minus half multiplied by zeta. Same way for hydrogen, same way for ammonia. Okay. So, you do that and then look at the end what are the number of moles that you get. So, the number of moles that you are going to get is x minus zeta by 2 something and something else. Okay. Now, there are two ways in which this reaction can be run. One is a constant volume reactor. Constant volume reactor means it is carried out in in a closed vessel, for example. Okay. If it is carried out in a closed vessel, the pressure might increase or decrease. In this case, what will happen? Is the pressure going to decrease or increase? Because of reaction, decrease. Okay. So, you have initially you have some number of moles, because of reaction the number of moles are reducing, because the number of moles are reducing. So, therefore, either the pressure will decrease at a constant volume or the volume will decrease at a constant pressure, okay, or both will vary depending on the conditions that are given to you. So, in case number 1, you have to do the case where volume remains constant and pressure decreases. Case number 2, where pressure remains constant and volume decreases. Okay. Delta G is given. From delta G, you will calculate K equilibrium. K equilibrium is e to the power minus delta G by RT. Okay. And K equilibrium and Kp have the same values provided the pressure is in bars. It is not the same, K equilibrium and Kp are not the same, okay, because Kp will have units of bar inverse, okay. K equilibrium is dimensionless, okay, the value will be the same if you consider everything in terms of bar, okay. So, you will essentially have one equation in one variable and you can solve that equation in a single variable under multiple different cases and you will get your result. In the second example, you have isomerization, you have 3 isomers. Okay, and you have K1, K2, K3, okay, and idea is that if you start with A and end with A, then your delta G is 0 because delta G is a state function. And that is what you will use to calculate your equilibrium constants, okay, and you can again solve it based on extents or you can solve it based on the final number of moles of A, B and C, okay. That is how you will solve your equations for the two problems. And the last thing that I will state is we are not going to actually solve these type of problems, but let us say you have a larger set of reactions as shown over here. Okay, let us say you have say 500 reactions in 50 species. Okay, how do you know which reactions are linearly dependent or linearly independent? Okay, there are mathematical ways in which you can do that, and what is done is basically you construct a stoichiometric matrix, and then you remember Gauss elimination. Vaguely we have done Gauss elimination in your past life, right? Okay, so when you do Gauss elimination, you can obtain what is called as a reduced row echelon form. Actually the Gauss-Jordan elimination, okay, and the reduced row echelon form will be I 0 0. The size of I is going to be equal to the rank of that matrix. Okay, last time we had said that these three reactions are not linearly independent, but indeed the third reaction is linearly dependent on the two. So therefore, the way that you will get this matrix is 1 0 0 1 0 0 0 0 0 0 0 0 A B C D 0 0 0 0 0 0 0. Oh sorry, A B and 0 0 0 0. Your A and B is going to determine how the reaction, the third reaction, is dependent on the first two reactions. Okay, there are standard processes that are there, that are available, whether it's MATLAB or Keras, or whether it is Python. There are there are subroutines or functions that are available that will convert it into row echelon form and then tell you, how the various columns are linearly dependent on each other. Okay, so you can do that for a very large system very efficiently. Okay, so that is what is done. So what we are showing you over here is just a slice of the concepts that you are going to use. Okay, if there is interest and there is time, we can look at some of these. These are usually advanced concepts that I tackle in the subsequent course. I don't do it in this course. Okay, for today, excuse me, all you have to do is solve these two problems and submit your tutorial sheet by today. Okay, alright. So you can start working. The class is too quiet. Not too many teachers tell you, you will hear them telling this. So discuss with each other, move around if you need to, and yeah, try to solve these two problems.